Here we're going to look at one more approximation method for the definite integral, and it's called the trapezoidal rule. And as you can probably imagine, it involves breaking up your curve into a bunch of trapezoids and finding their area. So you'll see that it tends to be a pretty good approximation, usually better than your LREM or RREM or even MREM. So here's how it works. Let's take a look at this curve here. Let's break it up into subintervals. So again, let's just pretend this is A and this is B here, and I'm looking for the definite integral, the integral from A to B of this function. So we'll call this x naught, and we'll break this up into a bunch of subintervals as usual. So we'll call that x1, x2, x3, etc. This could be x sub k minus 1, and that'll be x sub k. This will be x sub n. X sub n minus 1, etc. And I'm not going to use function notation. I'm actually going to call this point right here x naught, y naught. Call that point x naught, y naught. Oh, sorry, x1, y1. By the way, you can ignore the scale on the left here, the 1, 2, 3. They're not really needed here. So I'm just labeling these points. Etc. And by doing this, you'll see that we can make some nice trapezoids. Alright, I think that's probably good enough. Well, I guess I might as well finish. Alright, so we get the idea. So now what we're going to do is we're going to draw some trapezoids. So I'll draw them in black. So your subinterval determines one of the base or the height of the trapezoid, and if you create these trapezoids, you can just get a sense of how they do a better job of catching much of the area, right? A better job than the rectangles are doing. So our goal now will be to come up with, I'll just draw a few random ones here. Our goal is going to be to come up with a nice formula for the areas of all these trapezoids. Alright, so let's just remind ourselves what the area of a trapezoid is, or the formula at least. The area of a trapezoid is the average of the two bases divided by 2, or the average of the two bases, that includes the dividing by 2, times the height. So our integral here, the integral from a to b of that function f of x, should be about equal to the areas of all those trapezoids added up. So the area of the first trapezoid, now you have to keep in mind these trapezoids are sideways, right? So the heights are actually, these are actually the heights right here. That's the height. That's the height. And we rigged them so that they're all the same. Right? Those are the heights. And the bases are actually vertical. So the first trapezoid has an area of h times the sum of the bases. Well, the first base is y0, y sub 0, and the second base is y sub 1. right? You can see that here and here. So it's going to be h times y sub 0 plus y sub 1 over 2. So that's the first trapezoid. The second trapezoid is going to be the height times its bases, which is y1 plus y2 over 2. Right? And so we just continue in that way. The next one's going to be the h times y2 plus y3 over 2. All the way up until the last one, which will be h times y sub n minus 1 plus y sub n divided by 2. And what you'll notice is that in each of these terms, you have an h over 2. So if you factor that out, what you're left with is y sub 0 plus y1 plus y1 plus y2 plus y2 plus y3, all the way up to y sub n minus 1 plus, I'm going to put this in, y sub n minus 1 plus y sub n. The reason I doubled that y sub n minus 1 is because you probably noticed that all those middle guys, right, are doubled. So that'll include the y sub n minus 1. And so now you can group those and say, well, this means that I can write it as h over 2 y sub 0 plus 2 y1s plus 2 y2s plus 2 y3s plus 2 y sub n minus 1s plus 1 y sub n. So that is the trapezoidal rule, and all it really does is allow us to find the areas of all those trapezoids really quickly just by plugging in the y values of whatever data we've been given. So you have to understand this only works if your interval is your subintervals are all of equal length. I've noticed on the AP exam they rarely give you questions like this where you can use the trapezoidal rule. They'll just give you subintervals that are not evenly spaced, and then you just have to kind of add up. You have to get the area of each trapezoid individually and add them up. But on the off chance that you have to use the trapezoidal rule and the intervals are evenly spaced, you can just use this formula here that I circled. So I'll do one example of it, and then there's not much more to say really. It's pretty easy to apply. So here we're going to apply the trapezoidal rule. I'm told that I need to estimate the integral from 1 to 2 of x squared, and I'm supposed to use n equal to 4, which means I need to make 4 subintervals. So if n is equal to 4, that means that I need to break up the interval 1 to 2 into 4 equal pieces. So the height of my rectangle is going to be 2 minus 1 divided by 4, which is 1/4. So here's 1, here's 2. So we'll cut that up into fourths. So this is half. So that's write that as 3/2. This will be 5/4, 5/4, 6/4, 7/4. And now I'll make my trapezoids. So I'm going to need these y values at some point, but since the function's x squared, it shouldn't be so bad. One thing to point out is that this approximation is going to underestimate, and that has to do with the concavity of the graph. So it's underestimating because this graph is increasing, and if it's decreasing, you usually will be overestimating. So I'll just quickly sketch that. Well, I guess I'll sketch it later. Okay, so to use the trapezoidal rule, we're going to say t equals h over 2. So h is 1/4. So it's 1/4 over 2. And then it's y 0. So y sub 0 would be this guy here. So this point here. This is x sub 0, and this is x sub 4. So the y value of that point is 1. And then I double everything on the inside. So what I like to do is I put a big 2 here and add up all those values on the inside, because we're just timesing them all by 2. So the next y value would be 5/4 squared plus 3/2 squared plus 7/4 squared and then that's the end of the ones that get doubled. I'll simply add that to 4. 2 squared, which is 4. Alright, and so now I'm going to trust that you can plug this into your calculator. You end up getting, I guess, 75/32, and that's about equal to 2.34375. And I've got the definite integral, the actual value of the definite integral up on the screen there, so you can see how close it is. So there's the trapezoidal rule in an application problem. Again, it comes in handy. It's a nice quick formula if you remember it. If you don't remember it, you can always just find the areas of each individual trapezoid. It's not that big a deal, but this is definitely a time saver if you find that you can use it.